We've spent a fair amount of time looking at what is known as ray optics or geometric optics, and in that kind of frame of reference, that paradigm, we're looking at rays of light traveling in straight lines. But the idea behind that is that light was actually particles, little jets of particles, and this dates back to Newton. Newton called them corpuscles, and he imagined these particles striking your eye and imparting a force on your eye, and that's what stimulated sight. And that idea held for quite a while, but today we will look at when it was finally overthrown. But before we get to that, we need a little bit of background here on some wave mechanics. One thing that is going to be integral to our understanding of light being a wave is what's known as Huygens principle. Now, Huygens lived in the 1600s, so he was around the time of Newton, and he didn't apply this to light, but this still helped us understand what waves do and how to recognize a wave. So his principle is simply that if you have a wave front, so you can imagine this like curved wave, just a big nice rolling curved ocean wave, every point along that wave, so it's moving forward according to these red arrows here, every point along that wave can be considered a source, a point source of circular waves. And what happens is if each of these points along the wave here emits circular waves that travel outward, those waves will interfere. If you remember when we studied waves about constructive and destructive interference. So you'll get destructive interference everywhere except right along the new wave front. That's where you will get all your constructive interference. Okay, so this is Huygens' principle. Every point on the wave acts like a point source. And this also explains why diffraction works. Also, if you remember this phenomenon that we looked at with waves, we described it simply as waves going around barriers. But if you think about this wave here, so the red things represent the rays, the ray picture, so we have waves traveling this way. The blue things represent the wave fronts, like you can imagine a big rolling ocean wave. Well, if you have a barrier here, you're going to block the waves behind the barriers, but these ones right on the edge here are going to be like point sources of spherical waves. And so right here, if you have a spherical wave released, it's going to travel out this way. Over here you've got a bunch of spherical waves, but they will interfere and give you your wave fronts back, whereas on the corner here you get them bending around the corner. And if we have two barriers, you get bending on both sides, and then you get them adding up to nice straight wave fronts in the middle. And if we get the barriers short enough relative to the wavelength of the incoming waves, then you just get, you can basically single out a single one of these point sources, and then you just get spherical waves coming out. And this happens with water waves and all types of waves. So here are waves in the ocean. It looks like they're kind of coming in at an angle. But either way, you've got these two openings here, and so these act as sources of spherical waves coming out from these non-spherical waves over here. And then these will interfere and give you patterns like so. Okay, so there we go. Now, a guy named Thomas Young, not until 1801, devised an ingenious experiment to look at light rays. And what he did is he had the sun's rays, and he had two very narrow slits here, and then he had a screen behind it, and he was going to see what he could see, right? And if light were made of corpuscles, if there was just particles streaming through the air, when they hit this screen, all of the rays that didn't pass through the slits would be stopped, and then just a couple of jets or streams would pass through the slits, and they would hit right behind. So this is what you would expect to get, or what physicists expected to get. Light traveling straight through. That's not very straight, but you get the idea. A little straighter? Anyway, you just have two streams making through, and you'd see two light bands on a screen behind here. Turns out that's not what we saw. It's not what Thomas Young saw. He saw several bright bands here. So this is going here in our question mark location, right? Instead of seeing two, he saw several bands. And this was quickly recognized as a wave phenomenon. And essentially what's going on is exactly what I showed you here with these waves being produced by two slits in an ocean wall. So we can imagine two slits here producing these wave patterns. And now if you had if you were able to see the light traveling through the air, you could see these patterns. But essentially what happens is we put a screen up over here, and we're only able to see what happens on the screen. So you have this wave pattern going, and you get bright spots where you have constructive interference, and where you have dark spots on the screen, those correspond to destructive interference. So anyway, you get a series of bright spots corresponding to the locations where the two spherical waves, or circular waves if you're just looking at 2 dimensions, interfere constructively. So that's what these bright spots here are all about. You've got waves coming out from behind each of these slits, interfering on your screen here constructively. There's a bright spot and a bright spot and a bright spot. And because they diffract around the barrier, so to speak, due to Huygens' principle of them being point sources, then you get light up here where you wouldn't expect it. You would expect light just to be here in the middle, but you can get all kinds of bands, and depending on how far your screen is, you can get a whole bunch of them. Okay, so just looking at that idea one more time, here is our ray picture. The rays would be traveling this way. In the wave picture, those would correspond to wave fronts that are traveling this way. And when they hit these two openings, they become circular waves. Those circular waves interfere constructively and destructively. So you'd get a bright spot here and a bright spot, well, you can't really tell unless you draw these waves. Anyway, you'd get a series of bright and dark spots corresponding to the interference pattern. And we can calculate pretty easily the relationship between the angle and where we are going to get a bright and a dark spot. So the reason why we get this interference is because the paths of the waves sometimes are the same length and sometimes they're different lengths. So we're assuming that the light had the same frequency that was incident on the slits, so the light coming through both slits was the same frequency and was in phase or in sync when it went through the slits. So as long as the path between the location of the slit and a given location on the screen is equal between the two slits, then those waves will still be in phase, and so they will have constructive interference. Crests meet crests and troughs meet troughs, and so you get a bright spot there. Okay, and it doesn't just happen in the middle. You could have an angle, theta, here, from the point between your two slits to the point on your screen, where the path length differs by exactly an extra wavelength, so that by the time they hit the screen, they are again in sync. But you could, on the other hand, have this extra distance here. So this guy travels this far, this guy travels that far. This little extra distance here could be off by a half a wavelength, and what that's going to do is it's going to get things completely out of sync, and so you'll get destructive interference, complete destructive interference, and so you'll get your dark spots at that location. And we can derive equations pretty simply to solve for this. So if we say, here's a little more easily, it's easier to see this geometrically. So if these arrays, so to speak, these lines coming from our slits are at the same angle theta, then the difference in the distance is given by this little segment here, which is the distance traveled by this ray minus the distance traveled by that ray. And that angle there is going to equal this angle here by a bit of geometry. And so if we take the sine of that angle, then that is going to give us opposite over hypotenuse. So sine of that angle theta. Now the opposite is the difference in the distance here. So that's d2 minus d1. And the hypotenuse is what we're going to call d. Too many d's going on here. This d with no subscript is the separation between the two slits. These d's are the paths from each slit to a given location on the screen. So our equation looks like this, d2 minus d1 over d. Well, as long as this here, which is the difference in the path length, is equal to a wavelength or multiple of the wavelength, then we are going to get a bright spot. So we can rearrange this, and we've got d sine theta equals, it's usually written with m first, m times lambda, where m is just any integer, any positive integer typically. Okay, so this is how we can calculate the relationship between where the bright spot is going to be located, or what angle you have to get to the bright spot, given the separation of the slits and given the wavelength of light. So m starts at 0 because you want a bright spot right in the middle, and so that'll give you an angle of 0, and then you've got n equals 1, 2, and so forth. Okay, to get the dark spots, you need this to be off by a half a wavelength. So instead of this being m times lambda, it's going to be m plus a half times lambda. So m plus a half times lambda. That is going to give us the angle to our dark spots, and equal sign in there. It's all written nice and neatly on the next slide. So here we go. There, nice printed equations for you. So this will give us the locations, the angles to the constructive interference and the angles to the destructive interference. And these locations where we have constructive interference, these are sometimes called fringes or bright fringes, but sometimes it's just fringes for short. By fringe we mean I don't know, a line, an area. So that's just the terminology they use. Now a lot of times, if you think about this picture again here, so this is the light source, and then here's our slits right in here, and we're producing this interference pattern of waves here. This is useful to get the angles, but usually we have some screen set up, and the location of the fringes on the screen depends on how far the screen is. If the screen's way back here, you know, we're going to have a light fringe here, and then the middle of the light fringe here, and the middle of the light fringe there. But if my screen is over here, that's going to move things a bit, right? The middle of this light fringe is going to be moved up to there, and there, and there. So it's going to, the actual pattern you see, the angles are the same, but the actual separation there depends on the length to the screen. And we can get an equation that's going to be useful that defines the separation of these slits, taking into account the distance from the slits to the screen. Did I say separation of slits? I meant separation of fringes. Anyway, so if we start with our equation here, d sine theta equals m lambda, and I'm going to rearrange that. So I'm going to say lambda equals d sine theta over m. Well, sine theta is going to be the angle to my bright spot, right? Okay, and I'll draw it over here. Can't really see it over there. Okay. So if I have a bright fringe right at this location, there is theta. This is the length L, and this is x. Now the way I drew this, it's not going to be too convincing, but so if theta is very, very small, then the difference between the length of the hypotenuse and the length of this adjacent side here, L, is going to be incredibly small. So we do what's known as a small angle approximation. Physicists actually love doing this. So sine theta would normally be x over h, but usually it's a lot easier to know L, so we're going to call sine theta x over L. So this becomes dx over m, that's an ugly m, ml. And then this is usually rearranged to solve for x. So you've got x equals L lambda times m over d. And so this is going to allow you to solve for the actual location of a bright fringe on a screen that is a length L away. D is still the slit separation for the double slits. M is still the number of the fringe you want. So here we have that wave applet that I showed you back when we studied waves, and I'm going to go ahead and turn it on here. So I've got a bunch of waves crashing into a couple of slits. You can't really see the waves up here, but what I want you to see is this double slit pattern. I've got two wave sources, and I get this interference pattern of constructive and destructive interference. Now this pattern will change a bit if I change my frequency. So I'll go ahead and change the frequency and then kind of reset the wave so it's easier to see. Now what happens if I lower the frequency, that means I'm increasing the wavelength. And when I increase the wavelength, I actually get more bending. You have more diffraction with a bigger wavelength, which is one of the reasons why sound diffracts around corners a whole lot more than light, because it's got a much larger wavelength. So anyway, frequency changes the pattern. The higher the frequency, the narrower the pattern, the less the bending of the wave in this case, which is light. I guess I never really got back to our story. So anyway, when Thomas Young did this and we saw this distinct pattern, there was no possible explanation for how particles, corpuscles, could have produced a pattern like this. So this was kind of the slam dunk, and all the scientists came around and said, okay, I guess light is actually made of waves. Newton was wrong all along. The story kind of changed a bit, because today we know that light behaves as particles sometimes as well, so he was kind of right. But anyway, definitely behaves very much like a wave in a whole lot of situations. Here's one other way of describing that interference pattern. Now this is showing the relative intensities of those different bright fringes. So the central fringe is sometimes called the central bright spot. It's always the brightest location, and each subsequent fringe gets less and less intense. So this means it's the brightest, and these get dimmer and dimmer. And that's simply because there's less and less of the wave that wraps around, and more of the wave interferes constructively, kind of straight ahead or at small angles. And as I showed you that this varies with frequency, what happens if you pass more than one color of light onto double slits? Well, they bend at different angles, and so it actually spreads out white light like a prism. And this is what Young's original double slit experiment did. He used light from the sun, which has all the colors, and passed it through slits and saw something like this. And here is a video of somebody recreating that today. If you're interested, click there and enjoy some more wave optics. Okay, see you next time.